G'day guys, this will be the first video of 3 that attempts to prove the work energy formula for you. In this particular video, we're going to be talking about the definition of work and how it ties together with something called kinetic energy. So before we get started on the calculus, let's quickly imagine that we have a particle just here, and this particle is of mass m, and let's say there might be several forces acting on this particle that force it to undergo some strange, complicated path. Okay, so this is its path and this is the particle. Well, by creating an axis, we can say at some time t, this particle is going to be at a position x and a position y. So a position x in the horizontal and a position y in the vertical. Now let's talk about something called work. I'm going to define work as this letter w, which is going to be equal to the integral of f dot dr, right? And this might seem like some arbitrary mathematical construct at the moment, but rest assured, by the end of this 3-part series, I'm going to provide intuition behind it. And in case you don't understand what each of these individual terms are, let me briefly explain them. F is going to be one of potentially many forces acting on your particle from one position to another position. And dr is your differential element vector. So in fact, if you want me to write it out for you, I'll write it as the integral of fx, fy, dot dx, dy. Okay, so this is your vector f, this is your vector dr. Okay? Now, in case you don't remember how to evaluate the dot product, remember all you do is you multiply the first 2 terms, and then you add that to the multiplication of the second 2 terms. So this is going to be fx dx plus fy dy. And because this is an addition sign, we can actually put the integral around that right now. Now you might be asking, well, what are the limits of integration? Well, what you do, because this is dx and dy, let's first imagine that this particle was at a position we will call position 1, which is x1, y1. And let's say at a later time this particle is at a position 2, and let's say position 2 is defined by a position x2, y2. In this case, the limits of our integral signs will be from x1 to x2 and y1 to y2. So this is how you would evaluate the work done by a force on your particle between 2 positions, right? And in some cases, especially in some physics classes, they actually ask you to evaluate the work by using this formula, right? We won't focus on that right now. What I want to focus you on is several other forces that could be acting on this particle, right? Let's, for the sake of generality, assume that we have multiple forces on this particle. Let's say we have a force here. Let's call this F1. Let's say we also have another force acting on this thing. Let's call this F2. And let's throw in a third one. Let's say that we have another force just here. Let's call that F3. And there could be many more, but let's stick with 3. By definition of work, the work done by your first force, F1, is going to be equal to the integral of F1 dot dr, right? That's just simply plugging in this definition. Likewise, you can say the work done by our force 2 on our particle between position 1 and positions 2 is going to be equal to the integral of F2 dot dr, okay? And you guessed it, W3 is going to be equal to the integral of F3 dot dr. Okay, now you might be a little bit confused, like what does work even mean? What's the intuition behind it? Rest assured, I'll get to that at the very end of this series, okay? For now, let me talk about another term called your total work. And as you'd imagine, your total work, whatever it is just going to be the sum of all the works acting on your particle. So it's going to be W1 plus W2 plus W3. Okay, and of course, if there were multiple other forces, you'd add them too. You'd add the works done by those forces too. And if there were other dimensions here, I'm simplifying this just to 2D, you would also include another integral fz dz here. I'm just proving this for the simple 2-dimensional case with only 3 forces. Rest assured, you can generalize this further. Well, what does this evaluate into? Well, you can actually play around with this by plugging in the values and evaluating the dot product, but I'll save you some time. If you were to mess around with all that, this will turn out into the sum of f, so that's f1 plus f2 plus f3, dot dr, okay? And the beautiful thing about getting the sum of f here is that we can now use Newton's laws. We know that the sum of forces acting on a particle is going to be equal to the mass of that particle times by the acceleration of that particle. That's what Newton said, right? And so we know that this can be evaluated further to be m times by dv dt, right? This is just Newton's law right here. And the beautiful thing about invoking this is we can substitute the sum of f into here. And I'll briefly talk to you about velocity shortly, but let me not jump the gun. This is going to be the integral of m dv dt dot dr. Now I'm going to make another small mathematical jump. Rest assured you can prove this yourself if you like by evaluating the dot products and simplifying the vectors into a scalar. But I'll save you the work. This will be equal to the integral of mv dot dv. Okay? All I did is evaluate the dot product and use the chain rule. Now, before I go further, let me quickly remind you what velocity is. So at some time t, let's say your particle's here, the velocity of your particle will always be tangential to its path. In this case, it'll look like this. This will be your velocity vector v, right? And v can always be written as vx in the x direction and vy in the y direction. That means it has a component vx here and a component vy here. Now we can also say that the magnitude, so that's the length of your vector, also written as your speed in this particular case, is equal to is equal to the square root of vx squared plus vy squared, right? So basically, let me summarize. Your speed, also your magnitude of your velocity, is equal to the square root of vx squared plus vy squared. Now, you might be a little bit confused where this comes into play. Trust me, it'll come into play shortly. Let me get rid of this because I don't want to confuse you into thinking it's a force. Okay, I don't have any space here, so I'm going to move everything up here. Let's evaluate the dot product and start simplifying this integral. This will turn into the integral of mvx dvx, right? That's when you evaluate the dot product, plus the integral of m vy dvy. Notice I've just evaluated the dot product. Now, what are the limits of integration? Well, to help you understand this right here is going to be your velocity of your particle at position 1. This right here is going to be your velocity of your particle at position 2. Clearly, at position 1, this right here, which I'm hovering over, is going to be vx1, and this right here is going to be vy1, this right here is going to be vx2, and this right here is going to be vy2. So our limits, because we've got dvx and dvy here, are going to be from vx1 to vx2, and from vy1 to vy2. Now, because we're going to now assume that the mass of our particle remains constant throughout its flight, we can suck m outside of both integral signs and evaluate the integral now. So we can write this as m times the integral of vx dvx, which is simply vx squared divided by 2, with limits from vx1 to vx2, plus, I'm going to suck the m out of here too, vy squared divided by 2, with limits from vy1 to vy2. Okay? In case you can't realize, y is a subscript here and x is a subscript here. I hope I'm not confusing you there. Okay, well, we can evaluate this now. We know this is just simply going to turn out into a half times by m times by vx2 squared minus, I was about to write plus, but it's minus vx1 squared. And we're going to add that to a half times by m, now we're dealing with this one, times by vy2 squared minus Vy1 squared. And let me continue up here because I'm running out of space again. Now the beautiful thing about what we're going to do next is we're going to be able to substitute the speed of our particles at positions 1 and 2. And we're going to do that by doing this small mathematical trick. I'm going to group these two terms together, and I'm going to group these two terms together. So this can be written as a half times by m. Let's group this one and this one first. It's going to be vx2 squared plus vy2 squared minus, don't forget the coefficients here are negative, a half m vx1 squared plus vy1 squared, right? And in case you haven't connected the dots yet, let me do it for you. This right here is your speed of your particle at position 2 squared. And if you don't believe me, let's do the maths. v2, so I'll write it with a little flick down here to show it's the speed, same thing as this, is going to be equal to the square root of vx2 squared plus vy2 squared, right? And if you square both sides, you simply get, so this is 2 here, this is going to be v2 squared is equal to vx2 squared plus vy2 squared, right? So we're going to do that for this case, and we can simplify this down to be a half times by m times by v2 squared. Isn't that beautiful? We've managed to get this in terms of our speed at our second point just here. And we're going to subtract that from, and we can do the same thing here. It's going to be a half times by m times by v1 squared, right? So we've somehow, using the magic of mathematics, shown that our total work is going to be equal to this beast just here. But we're not done. We can simplify this even further. And what I'm going to do is I'm going to define another thing. I'm going to define something called kinetic energy. Kinetic energy. Sometimes written as a capital T, but I like to write it as KE, so I know it's kinetic energy. And I'm going to define it by KE is going to be equal to a half times by m times by your speed of your particle at any time, squared, right? And you can see why I want to define it like this. It's so I can simplify this expression above. So you can see now that your total work on your particle between positions 1 and position 2 is going to be equal to your kinetic energy at your second point. So this is going to be your kinetic energy at your second point subtracted from your kinetic energy at your first point. Your kinetic energy at your first point. And we can simplify this even more because this is your kinetic energy at your second point minus your kinetic energy at your first point. We can write our total work. Our total work is going to be equal to your change in kinetic energy. Wow. What a crazy result. Okay, now rest assured the intuition might be eluding you at this point. By the end of the third video, I plan to describe to you some intuition. For now, we've talked about kinetic energy. In the next video, I'm going to be talking to you about gravitational potential energy. And in the third video, I'm going to be talking to you about elastic energy. Cheers.